Hi, everybody. My name is John Rigney, and I'm a scientist that works in the Office of Animal Welfare, Ethics Strategy, and Risk at GSK. I work in the
let's take a look at this, and this is going to be a very high overview, and this is going to be kind of the continuation for the entire talk, how we think about things, okay? So I'm a statistician, so I have a very naive view of things. So don't get down on this if this is too simplistic. But what are some of the usual characteristics that we think about in these preclinical animal studies? Okay, well, typically there are multiple dosing groups. You could think of, you might have a group that corresponds to a control, a low, a medium, and a high dose group of animals. Typically, we're studying them across multiple dosing time points. Okay, so you might have a 7-day study where you dosed an animal, and then you follow it longitudinally for 7 days to observe outcomes, or maybe it's a longer study, but there could be, longitudinal component to it. And the biggest thing, which is probably the hardest hurdle in trying to reduce the number of animals, is that we already start with very small sample sizes, right? A typical arm or dosing group in a study could have, as small as 3 animals. And if you're lucky, and when I say lucky, I think of this as like, from a statistical point of view, you get maybe 15 animals, but maybe that's not so lucky for the animals, right? And so maybe on average, you have maybe up to 6 animals per group or so, 6 to 10. But these are some of the characteristics, but conceptually, it just boils down to something like this. You have one group of animals who's going to receive one treatment, call it this red syringe, versus some other group of animals that's going to receive some other treatment, called this blue syringe. You could think of this red syringe maybe as the treatment. This red syringe is maybe the control, okay? And you want to give it to both groups of animals. You're going to maybe watch them over multiple time points. You have 5 animals per group. And then at the end of the day, you're going to collect a bunch of outcomes, and you're going to say whether or not this treatment was effective, was it toxic, what happened. Okay, that's the basic setup here. Now, what I'm going to argue for this talk, and if you want to tune out now, this is the slide after this. You never have to think about another thing in some sense, but I'm just kidding here. But the proposal is stop dosing all of the animals all at once, okay? And start doing this. And what I mean by this is dose one animal at a time. Think of doing this sequentially, okay? You dose this first animal, you wait, you observe all of its outcomes. If you think you need to continue on, you dose a second animal, you dose a third animal, a fourth, etc. Okay? I could stop the talk here in a sense and not talk anything about statistics, but we're going to go there. But when you think about this seems like a very rational thing to do, okay? If we were to just think about, rather than dosing all animals at once, start dosing them in a sequential manner, you can easily reduce the number of animals that you have to use, even without statistics, right? If you can draw conclusions 1 animal at a time or some number of animals at a time, you can easily stop your experiment early rather than dosing all of the animals at once and then waiting to see what the outcome is, okay? But we're going to do this with statistics to make it a little bit more rigorous. So the problems here, right? So continuing on with the motivation, there has not been enough effort from statistics community with regards to the 3R. This is in my opinion. I mean, if you Google 3Rs in statistics, not much comes up. There's very few papers out there that have focused on this. I think this is slightly changing now, which is a very good thing. But I think there needs to be more efforts from the statistics community with regards to 3Rs. And this is part of why I wrote this paper and worked on this project, was just again in this idea of how do you make things more reproducible. It's pushing the needle, pushing the envelope, kind of moving things a little bit. I don't have to solve the entire problem, but I got to get the community going in the right direction. The problem we have here, right? Fixed sample size can be very wasteful with regards to the number of animals used, especially when large effect sizes are present. Okay, so we all know this, that if you just fix a number of animals from the get-go, you do some sort of power calculation, and in these early research stages, we're almost never powered unless you have, a large number of animals or you're expecting to see a very large effect size. And so if you think that, well, I am going to see a large effect size, why would I even have to, gather a lot of animals? It's very wasteful. It's not practical. And a lot of times what we find in the literature, and probably even within our own companies, is that, well, selecting the final sample size a priori, it's error prone, and it's often just based on defaulting to historical numbers. Okay, so I found a protocol from one study that somebody ran, and my study is going to look more or less the same. Let's just run it the same way. Let's pick the same number of animals. Okay. And this is not a very strong rationale, obviously, right? You have to take some considerations. You have to think about the design. How are you doing this? You have to make these considerations. And so these are some of the problems we encounter in a typical preclinical animal experiment. And so the solutions that I'm going to propose today is that we cast the problem in a Bayesian framework. We're going to leverage what I'm going to describe in a little bit, Bayes factors for the decision-making process. And under this framework, we can use what I'm going to call a sequential testing paradigm to actually do this. And it's going to allow for optional stopping of the experiment. Some spoiler alerts, okay? So some of the advantages. So if you were to carry out this sequential decision-making process, it's just a better experiment, right? From the sense of it matches how we think about doing things in our everyday life. So it should resonate with everybody. If you think about, some process that you do just in your regular normal life, you don't go out and you just, put all your eggs in one basket. You might do something a little bit and then you see how the outcome was and you do it a little bit more and you do it a little bit more and you get better at it. And so we shouldn't really be thinking about these things as, like a one-shot experiment, everything hopefully works. We should be doing this in a sequential process or sequential fashion so that we can actually learn about things. Another advantage is that we can optionally stop the experiment early when either futility or efficacy has been shown. So this is like to say that, if you had a control arm and a treatment arm and you're dosing animals sequentially, if it looks like the treatment works for whatever your outcome of interest is, then you just stop. You don't have to keep dosing more and more animals, Or if there's clear signs that it's not going to work, well, then you could stop for futility, okay? So you have this option of stopping early to try to reduce the number of animals used. In the paper, we show that, on average, and it kind of depends on how many arms you have and what you're looking at, but you get an average reduction of about 3 to 9 animals for a given experiment, let's say. And I'll show some examples of that. So there are costs or animal savings here. And one of the cool things, which I'm not going to talk about in this talk, and it's addressed in the paper a little bit, but you can incorporate prior, or if you've never heard that word before, historical information into your analyses, right? So we're taking a Bayesian approach. This allows us to carry in prior information. And so, it's a really nice way to think about things. Again, it kind of matches the way we work in our everyday lives. You learn something and you carry that forward into your next thing, right? You don't just disregard, your prior history and say, I'm not going to learn from things in the past when applicable. Okay, so some methodology. So Bayes factors. So very brief slide, and there's a handful of slides with math. Don't get bogged down in them. Hopefully the ideas that you take away matter more than the actual technical details. But what a Bayes factor is it's a way of allowing us to judge our posterior beliefs about one model or one hypothesis given the data versus your other model that you might assume, okay? And I'll give an example of what this means, but I should also back up and say what a posterior belief is, right? So in typical statistics, what we might call classical or frequentist statistics, you collect data and all of your inference and your prediction and everything about that data set comes from the data at hand. When you apply Bayesian thinking to this type of problem, you incorporate what I just called earlier a prior, so prior distribution, prior information. And so you take the data that you've collected, you have some prior beliefs of how you expect the world to work. When you combine the two, you then get what would be your posterior beliefs, okay? So this is like, how do I think about this after, I have some initial way of thinking, I collect data, and now I have some new updated belief about this, okay? So what I have written here is how you calculate the Bayes factor, and what it's telling you is, well, I have some posterior probability of my model or my hypothesis given the data, and I have some other posterior probability of some other model given the data. And here we can think of this as, the model for the treatment arm. This is the model for the control arm. This is just your data likelihood part. And this is the prior that you place on, your model one and your other model. What this really boils down to is you could think of this as the posterior odds. Okay, so this is the posterior odd of model one over model zero. Okay, so the treatment to the control, if you want to think of it that way. And it's just equal to the Bayes factor. So this part here is the actual Bayes factor times your prior odds. Okay, so you have some initial belief about how much more likely model one or the treatment is over the control. You collect some data for that, and then you get some updated belief about that, some updated odds. Okay, so the cool thing here is that when we use Bayes factors, okay, something that comes out of this, and this is completely true about the Bayesian paradigm, is you can actually make inference or probabilistic statements about null hypotheses. Okay, so if you think about this as, model one could be or you could call this hypothesis one, is, the probability of the alternative being true, that, maybe there is an effect present, versus the null hypothesis that, there is no effect, no effect present. Okay, Bayes factors and Bayesian statistics in general allow you to quantify the probability of actually saying the null is true. Whereas in classical statistics, we always think of this as, failed to reject the null hypothesis. I haven't rejected it, but I haven't also accepted it. Okay, I just failed to reject it. But Bayesian statistics gives you a way of actually quantifying evidence for and against the null. So it's a cool thing, and it's a nice little property that kind of falls out of this. So at the end of the day, though, right? You go through this calculation, and there's some steps to it, and I'm not gonna show those. You can see those in the paper, or you can find your favorite package to actually calculate them. But you have to calculate the Bayes factor, okay? And the Bayes factor at the end of the day is just some number, okay? And so probably should have rewrote this, but you can think of this as, right, the Bayes factor is actually the posterior odds divided by the prior odds, okay? So it's a change in posterior odds to prior odds. And so at the end of the day, it's just a number, okay, that comes out of this. There are lots of different heuristics for what that number means. I chose in this, for this talk and in the paper to just kind of use one of the more commonly used one. People kind of bracket these things slightly different. You pick your favorite one. But so if your Bayes factor came out to be, say, 1, that's telling you that there is no evidence that there's a difference, say, between the alternative model and the null model. Okay, so there's no difference between there being a treatment effect versus no treatment effect. If it's all the way up at 100, then that's extreme evidence for the alternative. If it's down at less than 1 over 100, it's extreme evidence for the null hypothesis. And there's a whole range of different types of ways to categorize it, right? Extreme evidence, very strong evidence, moderate, anecdotal. You could think of this as saying, if your Bayes factor came out to be 10, you could say that the alternative hypothesis is 10 times more likely than the null hypothesis. Okay, so if you're comfortable with, say, odds ratios or hazard ratios, it has that same flavor of interpretation. Some people don't like that, and here's some categorization that you have to kind of live with in some sense, okay? But this is like an evidence threshold, right? So when we go to calculate a Bayes factor, this is the level of evidence that I am claiming that, I might need to show that, say, the alternative hypothesis is over the null hypothesis. It's 30 times more likely than it. So how do we actually use this, right? So I told you now what a Bayes factor is. Hopefully that made sense roughly. But now we have to incorporate the sequential part to it. And it's very simple, right? So we're going to conduct a sequential experiment where optional stopping of the experiment would be evaluated each time when an animal is added to the experiment, right? So we run our experiment, we dose, imagine you only had 2 arms, right? A treatment arm and a control arm. You dose a treatment animal, you dose a control animal, you collect the data, and you keep going, okay? One at a time. At every step, we're going to calculate the Bayes factor, okay? So I dose 1 animal in each group, I calculate a Bayes factor. I dose 2 animals in each group, I calculate the Bayes factor, and I keep going, okay? And so under this paradigm, you would say, I choose my level of evidence to, say, be 30. My Bayes factor needs to be 30 to claim that I want very strong evidence that the alternative hypothesis, that there is an effect present between the 2 groups, to be my stopping criteria, okay? So you would calculate your Bayes factor sequentially, and when you finally hit that bar, so let's say 30 in this case, you stop your experiment. You have enough evidence. Or vice versa, you could have, the evidence bar in favor of the null that, so this is kind of like the efficacy bar. These numbers down here are the futility bar, okay? So if I get something, say, as low as 1 out of 30, that's strong evidence that there's no effect present. I should just stop. I should stop wasting animals. I should stop for futility. Okay? This acronym here is the null hypothesis significance testing. So this is, the classical hypothesis testing under the frequentist statistics. In this paradigm, so in the non-Bayesian paradigm, optional stopping, like I'm describing, the sequential nature, is discouraged because it leads to an increased type 1 error rate. Under a Bayesian framework, this is not a concern here, okay? There are ways to kind of control these error rates. There are properties of Bayesian statistics that, it's a sequential learning procedure, and so there's no actual issue of type 1 error. Type 1 error actually doesn't even exist from a Bayesian point of view, which is why it's not a concern here. But it's one of those things where we don't have to be concerned about how many times we look at our data. We can check the type 1 error rates, and I'll put them in quotes because, again, I said it's not really defined. And we do that, and I'll show you what they come out to be under a Bayesian framework, okay? If either level of evidence is not achieved, then we simply carry out the experiment based on the full sample size budget, okay? So if I said I need a bar of 30 to stop my experiment in, favor of the alternative hypothesis, or I needed a bar of 1 out of 30 for the null hypothesis, there's a chance that I never hit this, right? I just fluctuate between values between, I don't know, say 10 and 1 out of 10 or some other range of values. And I never actually get it there, right? So I may actually end up using up all my budget, but at the end of the day, I still had a chance to stop early. And at the end of the day, even though I ended up not hitting one of these bars, I still do have a conclusion, right? Maybe I'm at 3.7 and I say there's moderate evidence for the alternative hypothesis, but it wasn't the bar that I set out to claim, that would be, the evidence that I want to see in my experiment. A note here, and this doesn't really apply, but this is just something like the blanket you put on yourself to make yourself feel better at night. In the asymptotic sample size case, and what I mean by that, right, is as we let n go to infinity, so our sample size just increases, which why I say, we don't have this, but it's a nice property. The Bayes factor does converge to either 0 if your null hypothesis is true, or to infinity, right? So this guy, if the alternative is really true, there is an effect present, this thing should blow up to infinity if you had an endless number of animals to test, and this thing should go to 0 if there is no effect, okay? So we know that it does the right thing as the sample size increases, but we're not in that case. But it's a nice property to know. This is my last slide of math, I believe. Bayes factors calculations, and I said this earlier, right? So the Bayes factor is just equal to the posterior odds divided by the prior odds. Don't worry about these equations for the non-statisticians who might be on the call. But if you are a statistician, and I'm going to give you a quick, just 2-second word on each one, right? There's closed form for everything in a sense. It's a very simple calculation. So the prior odds is just equal to this integration over your joint prior, which we assume to be independent a priori. Okay, and then because there's only 2 groups, because it's a Bayes factor, it's just 1 minus that probability. And then the posterior is an integral over the domain of interest for the joint posterior distribution. Okay. In our paper, we said that, if we thought of theta 1 and theta 0, so this theta 1 could be the response rate in the treatment group, and this could be the response rate in the control group. We allowed it to be a beta 1,1 because this is a non-informative prior, okay? So we're not injecting, in the paper at least, how we did it. We did not inject any information about the response rates. And that seems like a sensible thing. If you want to take a very objective approach, so the one criticism of Bayesian statistics is that it's highly subjective, in that you get to have prior information injected into your analysis. So if you wanted to stay as objective as possible, you might want to try to use a prior that is non-informative, okay? So something that doesn't carry a lot of information. So this beta 1,1 turns out to be a uniform 0,1, and so there's no information about those response rates here, okay? You could obviously inject prior information that's very strong and reduce the number of animals needed in an experiment greatly, but we didn't do that in the paper. Okay, so some examples, and I'm going to show some simulation studies first, and then I'll show 2 real examples. So imagine we simulate some data, and here in this picture, okay, we have simulated 10 measurements, each for a control and treatment group from 2 Bernoulli distributions. Okay, so this is a distribution that requires a response rate, right? So One distribution is going to have the proportion of responders called theta t. So this is the response rate in the treatment group. And then theta c is the parameter for the other Bernoulli distribution, which is the response rate in the control group, okay? So I'm simulating with some known value of theta t and theta c, and I think I set it to be something around 0.8, and this one to be around 0.2. Okay, so this is like saying the probability of seeing a response in the treatment group is about 0.8, and the probability of seeing a response in the control group is about 0.2, or you could think of those as proportions. Okay, and so in this picture here, let's just think about this now sequentially. As we gather data, okay, so the y-axis here is the proportion of responses, and the x-axis is the number of animals I'm using per group, okay? Little triangles are treatment group, circles are control group. So right here, I've collected 2 animals, and maybe right away I see that, there's a response in 1 out of the 2 animals for both the treatment and control. So I have a 50% response rate. Then at 3, I see a response in both animals, and so it grows up. And then at some point, I start to see less responses in the control group and more responses in the treatment group. And then by the time I get to my 10th animal, I have something like 90% of my animals responded. And then, 20% of my animals in the control group did respond. Okay. And so a typical hypothesis we might want to test is whether or not, the treatment actually has an effect here. Okay. So we might think of this as, so the alternative is when we have an effect present. So maybe, we think about this as, is the response rate of the treatment group greater than the response rate of the control group, okay? And alternatively, the null hypothesis of no effect would just be that the treatment group response rate is less than or equal to the control group. So now, if we were to do this using Bayes factors, or I should take a step back. So I said here, I showed you how it would have progressed hypothetically, simulation, right? If we had collected the data sequentially, okay? If we hadn't done this under a Bayesian paradigm, we would have just done some test. And, the classical test for small sample sizes is do a Fisher exact test for 2 groups. So we could do a Fisher's exact test to test this set of hypotheses, and that would be fine. And so that's what we did. Fisher's exact test, it gets a p-value of 0.0002 at the expense of 20 animals, right? I get a significant result, but I've killed 20 animals. I've used 10 in this group, 10 in that group, and I killed 20 animals. But could I have saved lives had I switched to the sequential Bayes factor analysis and came to the same conclusion, okay? So let's say, for sake of argument, I say that my threshold for the Bayes factor is I need a Bayes factor greater than or equal to 30, okay? I want the alternative hypothesis to be 30 times more likely than the null hypothesis to be true, okay? That an effect is present in the treatment group as compared to the control group. This is the same plot that I just showed on the right-hand side, but the left-hand side now is a calculation of the Bayes factor on the log scale, just for simplicity so that it fits all into the plot, and the number of animals per group on this axis, okay? So like I said, at 2 animals, I have a 50% response rate in both groups. And so my Bayes factor is some value close to 0. If I was to sample 2 more animals or test 2 more animals, my Bayes factor still is down around 0, right? Because the response rates are basically the same here. And then as these response rates start to separate, my Bayes factor starts to grow, right? And this dashed line, if you can see it, this corresponds to a Bayes factor of 30, okay? So once my Bayes factor crosses this line, I could stop the experiment and say, okay, I'm done. I've reached the bar, the level of evidence that I needed to say that, the alternative hypothesis is 30 times more likely than the null hypothesis, right? And so it happens at 7 animals per group, right? So we cross the Bayes factor threshold after 14 animals. And so I would have came to the exact same conclusion as the classical testing method, the Fisher exact test, but with 6 fewer animals, okay? So there's clearly a reduction in animals, there's the saving of lives, and that's meaningful. You could argue with me now, you could say, well, let's back up. What if I had observed those response rates in a different order, right? I don't have to collect the data in this fashion. I could have seen, if you think about labeling each animal 1 through 10, I could have seen the 9th animal first rather than seeing the 2nd animal first, or some other order of animals. That's completely correct. we are prone to this, right? That, however you receive the animals is how you're going to stop your experiment. And so a different collection strategy would have led to maybe a different outcome. And so in this next simulation study, I basically simulate this exact same scenario 1,000 times to see how often do I still come to this conclusion that there's a difference with the evidence bar of 30, okay? So now let's consider running that same simulation 1,000 times. If I was to calculate the true positive rate, and how I'm defining that here now is I know that there is a difference between the treatment group and the control group, and I run 1,000 simulations. How many of those simulations are going to give me that I detected a true or a Bayes factor greater than 30? Okay, so if I ran this thing 1,000 times, 67% of the time, I would actually conclude that there is a treatment effect, okay? It's not 100%, which we would like, but that's the name of the game, right? There's also a false negative rate, okay? So true positive, that's a good thing. False negative, that's a bad thing. We don't want any of those. And so it's actually extremely low. It's pretty close to 0%, right? So this is actually telling me that 2 out of 1,000 times I would have actually claimed that the null is actually the truth, okay? When I know there is an effect present. So 2 out of the 1,000 times. That's really good. That's a really good characteristic. But now you could add those up. They don't add up to 100%. 32.9% of my simulations remain inconclusive. And what I mean by that is if I used up my entire budget of animals, 32 or 33% of the time, I would not have came to a conclusion that I could get over a Bayes factor of 30, okay? Doesn't mean inconclusive in the sense it doesn't mean that I can't draw a conclusion. Who knows? Maybe the Bayes factor is up at 28 or 29. It just never crossed that barrier. But as a good statistician or a good scientist, we should always think about how we think about these things where we pre-specify our values, right? We want to set the Bayes factor up front and say it's 30 and not change it later. So when you get to 10, you do have a quantification of how more likely the alternative is to the null, but it wasn't what you set out to prove, and so we shouldn't draw conclusions per se. So this is why I say it's kind of inconclusive. But the nice thing is, for those 67% of the times that I did do the right thing, okay, the average number per group was 5.5, okay? So about 12 animals on average are being used, or 11, however you want to think about that. But about 12 animals are being used as opposed to 20, right? So on average, I'm saving about 8 animals when I do the right thing. So I could also run this exact same simulation, and I did 1,000 times, under the null hypothesis. So assuming that the response rates in the treatment and control group are exactly the same. There's no difference, okay? My true negative rate, I want this to be extremely high, right? I want to flag all the times that I think the null is correct. I only do it 11.6% of the time. It's not great, but again, the one nice characteristic to take out of this is that the false positive rate, so the rate at which I'm claiming things are different when they're really not, is extremely low, right? It's less than 1% of the time. This is a good one. So again, you add these up, they're not 100. That's because 88% of the time I get inconclusive results, okay? So when I get all the way out to my 10th animal, my Bayes factor is some number that doesn't give me a conclusive result. And it makes sense, okay? When an effect is present, and this should just make common sense when you think about how we do sample size calculations in general. If you have a large effect size or any effect present, it takes some number of animals to decide that, right? But as that effect size gets larger, it takes fewer animals. But if there is no difference between the two groups, right? So the effect size is essentially 0, it's very small. It takes a lot of animals to be able to decide that's the truth, right? And so I'm not doing the wrong thing here, but it's very hard to actually do the right thing as well, okay? I do it sometimes, but all I'm taking from this is that, well, I have too high of a bar set to try to conclude the null is true, right? When my effect size is extremely small, right? So if a Bayes factor of 30 just might be too high for 10 animals per group. You may have to go with something lower if you were considering, wanting to stop for the null for futility. Okay. This is the exact same setup again, but I want to show you one more picture to really ingrain on you what these Bayes factors look like when you collect them sequentially, okay? So here, just for the sake of being able to plot things, I generate 100 data sets here, okay, where I let the control group come from some Bernoulli distribution. So the response rate for the control group is 25%, and the response rate for the treatment group is going to be around 70%. And so I'm going to sample from these two distributions for the control and treatment 100 times. And again, I'm going to assume the same set of hypotheses, and I'm going to set my Bayes factor to be 30, okay? And so why I'm doing this now is I want to show you how many animals you actually would need to collect. So I'm going to imagine I have an infinite budget to actually be able to come to some sort of conclusion here, okay? So under the alternative, so this is saying that there is an effect present. The treatment group response rate is larger than the control group response rate, okay? What I have here is a picture of individual trajectories. So these gray lines are trajectories of my Bayes factor that are being collected sequentially, okay? So I went out to say, you know, almost 40 animals here. And so if I set my Bayes factor to be 30 as the bar that I need, each one of these lines is one of the simulated experiments. So it goes up, it goes down, and at some point it gets up to 30, and this is where you see a dot, okay? So this would say like, you know, this dot here corresponds to maybe 8. It took about 8 animals per group to come to that conclusion. You get a bunch of different fluctuations. Even sometimes they get very down low, almost, you know, stopping for the null at 1/30. But this thing fluctuates around, and you get a distribution, right? So this is the sample size distribution. And so on average, you know, probably we're getting some number of animals close to around 7 or 8 per group. You might actually require you to get out all the way to 40, right? Remember my simulations where I said, you know, there was 33% were inconclusive. Well, that's because we stopped at 10. This is the extra 33% here, okay? And so when we look at this picture, we say, well, maybe a Bayes factor between 5 and 10 would have seemed optimal, right? Had I chose a Bayes factor that lived somewhere between 5 and 10, I would have came to the correct conclusion with, you know, at, you know, much fewer animals, probably by 20. But I would have kept the false negative rate around 0, right? Because none of these guys really, except for this one instance, gets past 10, right? So everything is around, you know, 1 out of 3, maybe 1 out of 4. And so there's a judgment call here, right? If I know I'm going to have a small amount of animals, maybe I can't set the Bayes factor as high as I'd like. Maybe I should keep it a little bit lower. Under the null, so when there's no effect present, okay, we could do the exact same experiment. So you want these bars, right, these gray ones to go downward, right? I want to have some very strong conclusion about the null being true, the no effect present. And so these guys are going down, they're going down. And you see this distribution, right? I said this earlier. The Bayes factor is set to be 1 out of 30, so very strong evidence. When you have a very small treatment effect or effect size, you need a lot of animals to be able to detect it, right? And here, the treatment effect is actually 0, or the effect size is 0. So the null is true. And so it takes a lot of animals actually to be able to do that, right? I mean, even out at 100, there's a couple of points that never actually even hit this bar, right? So about 7% of my simulations were actually inconclusive, all the way with 100 animals per group. And the average sample size actually is about 40 animals to come to the correct conclusion. So testing under the null is a much harder problem. That's the takeaway here. Detecting things under the alternative is a much easier problem, and that should intuitively make sense. There's even more of these operating characteristics in the paper, so I'm not going to belabor the points here, but I would just, you know, advise you to go look at the paper if you wanted to see more details. But the key takeaways from the paper were that larger evidence bars require more animals, just like I said, right? If you want to set your Bayes factor to be 30, you need more animals to show you have a very strong evidence. In general, sequential Bayes factors lead to using fewer animals as compared to classical hypothesis testing. And we did actually compare it because you might say, well, there's also things like group sequential design, which fall into the classical hypothesis testing. We also compare it with group sequential designs, and the sequential Bayes factors still actually outperform them as well. When an effect is present, the true positive rate, or you could think of that as being the power, it was higher for sequential Bayes factors as well as we get, lower false negative rates. So this was something I showed a second ago, but it's in more detail in the paper. And when an effect is not present, so when the null is true, the false positive and true negative rates, they're actually comparable to other methods, like using, say, the Fisher's exact test, or using some group sequential design. So the other thing that's very nice about this is, even though you might think to yourself like, hey, this performance doesn't look so great, this is actually the same type of performance you actually get out of doing a classical hypothesis testing framework. Okay. So you actually still get the same types of false positive and true negative rates as doing the classical approach, but you actually you're able to do that with actually fewer animals, and we show that in the paper. So if you're interested in any of these extra details, please go check out the paper. Okay, I have two quick examples. So this is preclinical data from 7-day animal studies. Okay, so imagine now I have 2 7-day studies in rats. Okay, each of these 2 studies are going to have 4 dosing groups. So there's a control, low, medium, and high dose group. This is what we published in the paper, and because of confidentiality and whatnot, this is a very stripped down data set, stripped down everything, and so some of this is a little bit hand wavy and made up in a sense, but take it for what it is. But let's imagine here now that weight loss acted as a surrogate marker for activity. Okay, so we're going to give a animal in the control group the control dose, the low, medium, and high get the low, medium, high dose, and then we're going to look to see, did these animals over these 7 days lose weight or not? Okay, and if they did, that was some surrogate marker for activity. And so what we want to test here now is we want to test comparing the low, medium, high groups against the control group. Okay, so is the response rate in the control less than? So the null here is that there is no difference, right? The alternative is that the control, sorry, this is slightly backwards, I guess. But so the control is the response rate in the control being greater than the other arms, given that the response rate is weight loss. Is that right? I have to think about that. Sorry, guys. So you could still think of this as you want to see a higher number of responders in the control group as compared to the other arms, given that the response rate was whether or not you lost weight or not. Maybe I'm saying this backwards, and I apologize here, but in interest of continuing on, let's assume this is correct. And I want to point out that this is a retrospective analysis for illustration purposes only. Okay, so we didn't actually set this up and run this study and actually do this in practice. This was me looking back at some old studies and just pulling something out that I could kind of work on to test out this methodology without actually putting it in practice and harming animals. Okay. Okay, so data set 1. So imagine now we give the treatment to the low, medium, and high dose groups, and then we give a control to the control arm, and then we decide whether or not there was a significant weight loss. Okay, so if it appears that the animals lost weight, they would be a response, and if the animals didn't lose weight, they would be a non-responder. Okay, and so you have the proportion, so you have the number of animals. So we have 8 animals in the control, 6 in the low dose, 12 in the medium dose, and 6 in the high. And then you have these varying, these are the counts of the actual responders, and these are the proportions. Okay. One extra detail here, which actually will be critical, is that, we could also make this assumption that there is a monotonic dose response, so if you see some response in the low, you really are going to expect to see a response in the medium dose and the high dose. Okay, so there is this monotonic relationship with dosing. Okay, for the sake of this analysis, we're going to set the base factor to be 30, so very, very strong evidence. And the level of evidence in favor of the null is actually going to be set to 1/30. Okay, so also very strong evidence. And so what you see here from this table here is the iterations are the number of rounds that you could think of this as, like, I collected 1 animal, I collected 2 animals, 3, etc. And actually, this is, I've collected 2. So we always start with 2 animals because you can't calculate a base factor with just 1. But you start with 2, then 3, then 4, then 5. So this is the number of control animals, the number of low animals, the number of medium, and the number of high. And this is the 3 different base factors, right? So the base factor comparing the control to low, control to medium, and control to high. Okay? So think about this practically, right? At round 1, I have 2 animals in each group. The base factor is 0.96, 20.55, 18.24. I've not gotten larger than 30 and I've not gotten less than 1 out of 30. So I would continue adding animals. At the next round, I have 3 animals in each group. Base factor is 1, 67, 79. Okay, so I've now crossed the 30. So I can stop the medium and high dose groups. Okay, so those 2 definitely show signs of activity, but this group still doesn't. So I've stopped these guys. So this is why I have no more base factors and these sample sizes don't change. But here, I then get to add another animal to the low group. And so then, you know, the base factor between the control and low group might be 0.98. Add another animal, 0.37. Add another animal, 0.11. And so here I might stop the control and low, okay? And so when I say both methods come to the same conclusion, this is under the assumption that in here, we are testing these hypotheses using a Fisher's exact test, okay? So if we use a Fisher's exact test multiply, we would have came to this exact same conclusion that there's a difference between the control and medium, control and high, and no difference between the control and low. 16 animals are used instead of the full budget of 32. Okay, so if you added up all of this total here, you would have got 32 animals, but we actually stop, and sorry, this table is misprinted. These should be 3, 3, 3s all the way down. But if you add up the numbers, you actually get 16 animals used instead of the full budget of 32. Okay. And I should actually say there's another typo here. This should actually be 0.01 because we want to be less than 1 out of 30. And so less than 1 out of 30 doesn't occur here. Sorry, this has got like a typo in translation. But so this is 0.01. But either way, we stop both all the groups early, okay? But we come to the same conclusion as the classical hypothesis testing. And you might say to yourself, well, you only collected 3 animals. Maybe that's not practical from a scientific point of view, okay? But if you weren't willing to stop early, okay, you could define a lower limit on the number of animals that you want to test per group. So maybe you say you keep enrolling until you at least have 5 animals or 4 animals or some number that is, you know, makes you feel more comfortable. The other thing is that when I first wrote this paper and first did this analysis, I actually thought 3 did sound a little bit crazy. I had a summer intern this summer, and he kind of went through these calculations. We worked on a different problem, but it turns out that stopping with a small amount of number in these situations actually makes sense because you're stopping for when you actually see kind of like a large effect size, but it's not so much that you need 3. It's easy enough to show an effect is present when you're only thinking about what the difference is between the 2. We're not actually trying to estimate well the effects in each group. I don't actually care what the effect is in the treatment versus the control arm. I just want to know that there is an effect present. It could be 0.9 versus, you know, 0.7 or 0.7 versus 0.5 or whatever. And so from this point of view, we don't actually need a lot of animals to actually detect the effect, okay? And so after a lot of headbanging, he actually kind of proved to me that this seems like a reasonable thing to happen. All right, a second data set. So in this data set, when you look at these percentages, you kind of get this idea that, you know, the medium and high are different than the control, and the low dose and the control are not. In this data set, when you look at these, the classical test would have told you that they were all the same, okay? And even just looking at the percentages across here, there's not really much of a difference here. And so this is kind of like the null model, okay? And you have your total counts here. There's 8 in the control, 12, 12, and 12 in the low, medium, and high group. All right. So I'm going to use the exact same setup, same base factor criteria as before, base factor greater than 30. I'm not going to go through these steps because we already talked about them, but just let's look at the decisions that we're making, okay? So none of these are greater than 30, but none of them are also less than 1 out of 30, so I would continue adding animals. Now I have 3 animals. I continue adding animals again, right? Because none of these are greater than 30, none are less than 1 out of 30. And I continue adding animals. And finally, I get to a point at which one of my base factors actually drops below 1 out of 30. Okay? And so you look at this and you might say to yourself, well, the other two are not less than 1 out of 30, right? But this is where I'm saying that let's assume we have this monotonic dose response, right? And so if I don't see a difference between the control and the high, I should not expect to see a difference between the control and medium and the control and low. And so using your scientific rationale or your scientific expertise, you stop the high group and then you say, well, I'm going to also stop the medium and the low group, dose group. Okay. So I stop the study and I conclude that all of them are in favor of the null hypothesis. Okay. And so if I had actually ran this thing out to its conclusion, I would have used 44 animals. But if you add up the numbers here, right, there's 5 in each group used. I only had to use 20, right? So I saved about 24 animals here. There's a lot. That's a big savings, right? And I would have came to the exact same conclusion had I run the budget out under the classical approach. You could also test M animals at a time per group, okay, to mitigate these sample size. So what I said earlier, right, was, maybe 3 animals might not seem practical from a scientific point of view. Well, another strategy you could take was rather than adding 1 animal at a time, you could say, I'm going to add, 3 animals at a time or 4 animals at a time or some other pre-specified numbers such that you don't just stop very early at a small sample size, okay? This also, actually, thinking about this later, this also would help maybe control for batch effects, right? If you think about it, the sequential nature of this problem, if you're adding animals 1 at a time and you're waiting, so potentially the animal that starts at the study versus the 7th animal who enters, they might be, kind of far in time. And so you might have some sort of batch effect in time. And so adding groups of animals might actually, mitigate the concerns over a batch effect. All right, conclusions. So just to wrap up, I hope by the end of this talk, you think that maybe the use of sequential base factors, they do reduce the average number of animals used in preclinical experiments. In the paper, which has more gory, exhaustive details, sequential base factors, they do achieve desirable type 1 and type 2 error rates, which we're always kind of concerned about, but it's in the back of our minds when we think about Bayesian statistics. So that's a nice property. Sequential base factors is capable of quantifying evidence in favor of the null, like I said, right, which isn't something that you normally get out of the classical approach. But there's no free lunch in this, right? I mean, it sounds great. We're getting good type 1, type 2 error rates. We're reducing the number of animals, but there has to be a cost, right? And the cost really is actually implementing the strategy in practice, okay? And there's 2 ways to think about this, why there's a cost, right? It's a fundamental shift in paradigm. This is doing something completely new, completely different, but there's also a logistical cost to this, right? If I want to run a 7-day animal study and I dose all the animals at the same time, I know that study ends in 7 days. If I now have to do it sequentially, I have to wait 7 days for each animal, right? And so these studies may take much longer, right? And there's considerations about running it at a CRO, having them implement it, whatnot. So there are practical issues with this in a sense, right? But it's, again, in the vein of the reproducibility argument, it's pushing the needle, right? It's moving things such that we're thinking about how can we do better? How can we do better science to try to, encourage people to do things a little bit differently and make things a little bit more reproducible, more transparent, more open, okay? So there's a DOI here. I'm sure these slides hopefully will be handed out at the end. So you can click on this or you can just Google the name of the talk and I'm sure it'll come up. And I'm going to end on just a future direction, okay? So the one criticism we got out of the, this paper when we went to publish it was base factors, and I don't disagree with this statement, they're kind of hard to understand, not just like how do you calculate them, but a base factor of 30 versus a base factor of 20, it's hard to kind of wrap your mind around that, right? To say something is 30 times more likely or 20 times more likely, yeah, I get that there's a difference there between 30 and 20, but how do you actually quantify that difference? It's a little bit hard. It's not the way most people, I would argue, naturally think about things. And so what we thought was, well, maybe we could actually reformulate this problem as a sequential decision-making process, but from the point of view of looking at probabilistic statements. Okay, so here again, my last math equation, but this is really just saying, what's the probability that I would observe some effect size that's larger than some value, right? So this is like the response rate in the treatment group is larger than the response rate in the control group. So I want to know what's that probability, and with some level of certainty, okay, gamma, right? So I need this probability of my effect size being larger than some value to exceed some probabilistic threshold, okay? And I think if you think about this, this leads to a more natural interpretation of how we think about things. If I told you I will keep adding animals until I say that the probability that the effect size is, greater than 10 is 99%, that seems a little bit more reasonable to people, to say like, oh, 75% versus 95%, even though it's on a probability scale, we still have some sort of natural interpretation of what that kind of means, okay? We are currently working on this problem. We've actually more or less have solved it, and we're working on a publication or a manuscript writing right now. So hopefully, if you don't like Bayes factors, but you like probabilistic calculations or those ways of thinking about it, it's the same idea, sequentially calculating probabilistic statements to make decisions, okay? And so hopefully the paper on this will be out in a bit. And so at this point, I'll say thank you, and I will take any questions that you guys might have.
Okay, thanks, Tony. That was a great presentation. We do have some questions in the from the audience. We'll go in order that they were done. Dragomir Dragunov had asked for your one animal at a time, and which treatment arm would you in parallel for clarification when there's more than one treatment group, for example, low, medium, and high?
Yeah, so I don't have an answer for that in the sense of, when we looked at it in the simulations, I just pretended as if, or even retrospectively taking that data set, I just thought of it as, allocate one at a time into each group. That could be a strategy, right? You could do it that way. But I would argue again, like, just thinking about if you had a monotonic relationship, you should do this scientifically, right? You should use your guys' scientific expertise. If it makes more sense to dose at the higher end first and then work your way backwards, then that would be your rationale. Or if it's one of these kind of tolerability things where you would want to dose at a low dose and then work up. So it's kind of one of those things where there's not really a real answer. It's really kind of like, would dosing one group first allow you to stop early, as opposed to dosing a different group in a different order? So it's kind of context dependent.
Okay, and then a follow-up to that question, Dragomir had asked, what if our response is not a clinical observation or a lab measurement? For example, it could be a histopath finding. Can we still apply this method?
Yeah, that's a good question. So I guess to be able to apply what I just showed, it needs the outcome, like I said, it needs to either be binary or it needs to be continuous. So histopath is one of those ones that's a very hard outcome to work with, and I know there's like lots of issues even just without like thinking about what it is in terms of like standardization across studies and all these different things. There may be a way to work with the histopath data, but it's not something that I would know about to give an answer to. If you could boil the histopath data down into some sort of continuous metric or value or some sort of binary thing, then sure, you could use it. But right now, the sequential Bayes factors, at least as presented, it only works for continuous and binary outcomes.
Okay, moving right along, we have a question from Brianna Gaskell. She says, I like this idea, but it's really about stopping when a large effect size exists. However, it seems you can still draw conclusions even if that thresholds aren't met. How to help scientists establish what their animal budget should be based on this method? Go with your distribution model you showed. Or I guess it's a
Yeah.
question part. Do you go with the distribution model you showed?
Yeah. I think I get it. I guess there's two questions there. You could still, like she said, you could still make a decision based on whatever the Bayes factor is at the end of the study. It's a little bit of cheating in some sense, right? Because it's kind of like the idea of like, you run your study, you get a p-value that is 0.06, and you said, well, I had said my p-value should have been 0.05, and now I'm going to reset it and say, it's some larger number, and I'm going to still be able to claim significance. It's in that vein where it's like we shouldn't change things at the end. But we didn't think about this problem, but it's actually in the binary case, it's a very simple problem actually to solve. So you could actually, if you thought about, very high level answer here, but if you thought like, okay, I had a treatment arm and a control arm, and I know that I have, say, a budget of 10 animals, you could actually enumerate every possible outcome of, one response, two response, three response, every possible like 10 by 10 outcome you get. And you could calculate the base factor under all of those different outcomes. And you could kind of basically calculate to see like, under what scenarios do I get a base factor that's going to be greater than 30? And so this would serve as the basis for a sample size calculation. Of course, you have to assume things here. You have to assume maybe like what is your response rates, and that might be the part about the distributional assumptions. So maybe you have some Bernoulli distribution with a certain response that you expect to see. You could also do this in the continuous case. It's harder to describe, but you could make assumptions just like a power calculation, simulate and calculate base factors and figure out when would you stop, what would be your sample size. So there is an analogous sample size type of calculation that you could do.
Okay, great. Dina Manseva asks, with a consistent need in decreasing the time so we can have the data sooner rather than later, how can we utilize sequential base factors approach?
Yeah, and so that again is one of these. That's the no free lunch part, right? For sure, if you are going to run these things, you're gonna almost definitely have slightly longer timelines. But that's not to say that they do have to be longer. Um, if you thought about, it could be shorter in the sense that you do stop with fewer animals, right? I mean, you could still come to a conclusion very early on, so the time might not be that long. You could also do it, instead of one animal at a time, you could do it 3 animals at a time and still come to an early stopping decision. Um, but it's one of those, it is the bane of this problem, is that you do have to think about how you actually do this logistically, and it is probably going to take a little bit longer, right? But again, this is also written with the perspective of the 3 R's in mind. So when I wrote this paper and I thought about this, I didn't actually care about the logistics. I said, if you really want to solve the issue of the 3 R's, you really have to put the animal welfare. So it's not about the company, it's not about everybody else, it's really the animals. And so this is a way to try to save lives at the expense of the company in some sense.
Okay. Susan Boland asks, how does this method work for tumor-bearing studies when you are looking for treatment response over time? Sequential dosing would be challenging based on randomization of the animals and vehicle group reaching endpoint sooner.
Yeah. So again, I guess that's more of a practical consideration. So there's nothing that says this can't be done. It's really whether or not your problem lends itself to this sequential strategy, I guess. So I don't have and I don't work in that area, so I don't want to comment on it too much, but it's one of those things where it's like you have to find the right type of study that fits into this framework. So it might not work for everything, right? Just because of the logistics, right? You need to be able to collect outcomes sequentially. And even like I said, there's a 7-day study, but that's the 7 days that it takes to run the study, right? I mean, there's even the addition of, collecting the data, cleaning the data, giving it to somebody to analyze. And so you do have these time lags in between. So, there are these extra bits that make the logistics a little bit hard. And so to answer that question again, I think it really is your study type needs to be able to fit the framework of sequential base factors. And so if the way animals get dosed or the way they get followed or, data is collected doesn't, fit into this framework, then there's not much you can do.
Okay. Christine Schnackenberg writes, I appreciate your comment about how this approach tells you there's a statistical difference between the groups, but not the quantified difference between the groups. A limitation of this Bayes approach is not understanding the biological relevance of a difference that is not quantified.
Yeah, sure. I don't actually disagree with that statement, right? I mean, the Bayes factor is telling you at least the way we presented it today, that tells you how much more likely. It's the same argument about, a p-value. It tells you that this thing is significant, but it really doesn't tell me what the effect size is or anything like that. When we wrote these hypotheses, I mean, you could think about this as theta t greater than theta c minus some delta, right? So you could incorporate the effect size into these statements. And so you could use your biological relevancy of how large the effect needs to be for these hypotheses to be true. That would still work. And actually, this is actually, I think, a reason why to switch to this paradigm here, or this framework, because here you are actually addressing, I think, what you're getting at is this issue of how do you specify delta, right? I want this response rate to be statistically significant, but I also want it to be practically different. I want this thing to be larger than some value. If it's, larger than 0.01, great, but that's not a big difference. I want it to be larger than 30 or something like that. So hopefully, I think if I'm interpreting that question correctly, there are ways of incorporating that.
Okay. We have a couple more questions. We have 3 in a row here from Layla, so we'll just go in order. First one that she asks is, how do we determine what sample size to include in a project for budgeting purposes and for ethics review if planning to use this Bayes approach? Just use power analysis and state the actual sample size could be smaller?
Yeah, so this goes back to that question I addressed, I guess, at the beginning, where there is an analog to power calculations in this sense. I wouldn't call it power per se, but it is like, you could enumerate all the different possibilities, and you could have some kind of prior predictive probabilities that you look at. And so it's not in the paper, and I wish now, having done this, spent time with this summer intern this summer, he kind of looked at this. I wish we had talked about this, but there are ways of constructing calculations for sample size out of this, right? And it really is kind of a simulation based approach, although in the binary case it is closed form, where you could figure out, how many animals would you need to achieve a Bayes factor so high.
Okay. And then Layla's next question is, can the same Bayes factor levels be used for experiments with more than 2 experimental groups? How is the Bayes factor level of interest decided at the project planning phase for such experiments?
Yeah, so it can. And actually, the more interesting point I think I'll make here would be that the Bayes factor doesn't have to be the same across the different groups, right? So I kind of just by default always use this high bar of 30, but you could actually use, control versus low, control versus medium, control versus high. Those are 3 different comparisons. You could have 3 different Bayes factors, right? They don't not have to be the same. And the Bayes factors don't also have to be the same. Like I did 30 and then I did the reciprocal 1 out of 30. The evidence in favor of the null could have actually been less. It doesn't have to be the reciprocal. So you have a lot of flexibility in this framework. How you choose that number is that's again one of these scientific discussions. Everybody sits together and you have to kind of debate it in a sense. Again, this is why I don't quite like this Bayes factor approach that we proposed, because it is a hard value to interpret and kind of quantify. You could potentially, if you thought about really trying to plan for this, you could look back at historical data, run this approach, and get kind of, what are the Bayes factors that come out of older studies to get an idea of like what is the level of evidence that these types of studies produce. But yeah, it's one of these, it's a judgment call. Why is 30 a high bar versus 20 versus 27? Who knows? I like actually moving to this probabilistic framework a little bit more because of these issues.
Okay, and I think you sort of hit on her third question is, what point in the experiment should the historical data be used if they exist?
Yeah, so we did not use any historical information. This is going back to, when I talked about the prior information, that we used an uninformative prior, something that was, uniform across the response rate. And that again is a tough question to answer, because it's one of these open questions that a lot of people actually, there's a lot of groups within the American Statistical Association and even within the IQ, I believe, that are working on this problem. And it's really, how do we leverage prior information? And there's not really a good answer. You can argue that, from a Bayesian point of view, you can always use prior information, but it's really showing whether or not that prior information is suitable. how well does that information, this historical information, really match the study of today? You probably have to do a lot of checking, summary statistics and just kind of process monitoring to make sure that like there's no drifts over time, that the animals of the past are the animals of today. How applicable are your study protocols the same? Is everything, is kind of like, it's a hard question, right? It's very context specific, and there's not a lot of guidance from regulatory yet, I would say, um, in this space that would tell you how to do this well, right? There are some Bayesian guidances in device development that talk about how do you borrow historical information in the clinical side, but the preclinical side is still kind of an open question.
Okay, and I think this is the final question we have is from Dragomir Dragunov again, follow up to a question he had. It says another
Okay.
one. Suppose we dose the animals as usual, but analyzing the results one at a time. We're not saving animals, unfortunately, but can test the approach.
What was the question in that one?
I'm not sure. I think he's just putting out he's proposing that they suppose that they dose the animals as usual and then analyze the results one at a time. That's not saving animals, but can test the approach. I'm not sure the question in that one, but
Yeah, I'll punt on this one. I'm not so
yeah.
sure.
He followed up below and says it is using legacy data for trying the method.
Oh, sure. I mean, and that's what we're doing in that case study, right? It's a retrospective study. This method needs to be I mean, this method is definitely grounded in theory and statistics. It's a fine method, but again, this kind of goes back to how do you practically implement it? When you think about this, I mean, I showed some very simple examples of how, if you had this data and you thought about, you collected it in a certain way, you could run the analysis. But I mean, the moment you really start to sit down, as a statistician, when I think about this, the moment I sit down with a preclinical scientist of any type, they're going to have so many questions, so many logistical things they're going to tell me that are going to make the running of this a little bit difficult or challenging, or it's going to make me have to rethink how I think about things, right? So you could go through this exercise of looking at historical data to try to see how well this would have worked, and you'll probably run into lots of implementation issues that are more practical, less statistical.
Okay, and I think that's it for the questions. And we are right about the limit there, 15 minutes over.
Okay.
So, Tony, again, thank you. This is a great presentation. The IQ will send out the links so you can watch it again, and I believe they'll send out the slides as well, or make the slides available. And if questions, I think you can reach out to Tony, we'll make that available, or you can read his paper that goes in over this in depth. The link will be sent out for that as well, or be in the slides or the presentation again.
Yeah. Thank you guys all for listening. I really enjoyed it.
Yep. Thank you very much, Tony. It was great.
All right. Thank you guys. Bye-bye.
Bye.